Let's now continue describing graphs. I assume everybody knows what a graph is. For the sake of this lecture, a graph is nothing more than a collection of edges and nodes, and it can be described in matricial form using the adjacency matrix. The adjacency matrix is given a labeling of the nodes, basically nothing more than a description of which edges are between which nodes. Say if the matrix element Aij is 1, this implies that there is an edge between the nodes I and j. Of course, we're using a definition in which the beta is equal to 0 means there are no elements of the diagonal, and so no self connection. But of course, this can be relaxed. Another way of describing a graph is via the incidence matrix. Unlike the adjacency matrix, the incidence matrix is L by n, where L is the number of edges while n is the number of nodes. A notation that I usually use is to describe with Greek indices the edges while or the links, and with a Latin indices the nodes. For instance, in the case of one little exercise is what is B transpose? What do you get in the diagram? Another thing you can, given the adjacency matrix or the incidence matrix, one key object in graph theory is the graph Laplacian. The graph Laplacian can be defined as the equation on the slide, and this implies that there are two equivalent definitions. One is via the adjacency matrix, where you define first the diagonal matrix called the degree matrix, and if dii is nothing more than a number of edges for a symmetric graph, for symmetric adjacency matrix, the number of edges are incoming or outgoing the node, and the Laplacian is defined as d minus the adjacency matrix. Alternatively, you can define it via the incidence matrix as B transpose multiplied by B. Okay. In general, the Laplacian has several properties we can describe, and it's used in particular for diffusions on graphs, random graphs. So what are the properties of the Laplacian? So given the fact that the definition of the Laplacian can basically be defined by the square, and here I'm using quote unquote, of the incidence matrix, this also implies that the Laplacian is basically a positive operator. And this is for the following reason. Suppose you squeeze between two vectors x and x transpose the Laplacian. It's not too hard to see that actually this is equal to the sum over all the possible links of the graph, where x, the sum of all possible links of the graph of xi minus xj, given the vector x. And this is a positive sum because the sum is a sum over square of basically the sum of positive quantities. This can be also generalized to weighted graphs. In particular, if the adjacency matrix, instead of being made of only 0 ones, it is made also of elements wij, it's not hard to see that actually you can define the Laplacian via these elements wj's, exactly like the second formula on this slide. The Laplacian has several properties that I'm now going to describe. Two that are, the first is straightforward, the second not completely straightforward is the fact that the trace of the Laplacian, which as we saw before, is the sum over the eigenvalues of the Laplacian, is actually equal to 2 times the number of edges or number of links of the graph. On the other hand, the trace of the square of the Laplacian operator, which is the square matrix, it's not too hard, which is the sum of the positive squares of the eigenvalues in the matrix is equal to the sum of the degrees square plus 2 times the number of edges. This implies um, that basically both the Laplacian and the square of the Laplacian has basically information about the degree and the number of edges of the graph. So how do you see that? So these are general properties of square matrices. If you have a matrix which is defined as the square root of two matrices, this is always a positive operator. For directed graphs, there is not a unique definition of Laplacian. Here we provide two different definitions. In particular, we can define because the graph is directed. Basically, you have two different definitions of edges. In particular, those that are incoming to a node and those that are outgoing a node. And then, given these two definitions that are basically described by either A or A transpose, you can define here the Laplacian L plus and L minus to describe two different phenomena. One is the forward phenomenon, one is what is called the reverse phenomenon. Um, the degree matrix can be defined by the sum over J of Aij for the incoming nodes, incoming edges, or D out the outgoing edges as the sum over J of Aij transpose. Given this, given the fact that actually these matrices are not symmetric, if you want to talk about the eigenvalues, it's actually a good idea to symmetrize it. There are two ways, well, actually, there are several ways of doing this. What you find usually in the literature is basically equations either 13 or 14. One is the nothing more than the average of between L plus and L minus, and the other one is the mean is the square root of the sum of L plus and L minus plus L minus L plus. Another graph is usually used in both in metric science and in graph theory is what is called a line graph. A line graph is basically the following construction. You start from your base graph. Let's say here would be the black graph in this figure. Now what you do, you just start to put nodes on each edge of this graph. Here there are the red nodes. And you connect these two nodes if the edges on the original graph here described by the black graph, they are connected through the same node. At this point, you remove the original graph and you're left with the red graphs in this slide. And that's the definition of the line graph. I like to use this definition where I use the tilde L for the definition of the line graph. One particularly interesting relationship is the connection between the incidence matrix of the original graph and the adjacency matrix of the line graph. Basically, you can write the adjacency matrix of the line graph as the square of the incidence matrix, but taken basically taken not in the multiplication, not in the same order as in the case of the Laplacian, but in the opposite order. This is a matrix which is L by L in dimension, which is the number of edges by number of edges, which makes sense when we're talking about the line graph. But you need to be careful and remove the 2 times the identity, because that's a number of times, that's a number that appears on the diagonal if you consider that only the definition. This is almost close to the edge Laplacian of the graph, which is another way of it's another definition based on instance matrix, the graph, and it's also in its own way, it's also a Laplacian. Um, okay, so something I wanted to mention is actually some properties of the Laplacian for the line graph. It's not too hard to see that if you add an edge to the original graph, then necessarily the Laplacian has to augment its by one row and one column. Okay, and this is simply because if you add one edge, basically you're in the line graph, you're gonna add one node. Then it's not hard to see that the last equation on this slide is true, which is the Laplacian of the line graph, the augmented line graph where we added one edge, is nothing more than the original instance matrix squared, exactly the same order, plus one term which is z transpose, where z is basically a vector, and this is a tensor product. It is basically a vector where the there's a one where the new edge was. Why do we use these? Do we need these properties? It's just because then we can discuss the properties of the determinant of the Laplacian. In fact, we can write the determinant of the full Laplacian of the characteristic polynomial of the Laplacian of the line graph, and rewrite these via the trick that I just described by adding and subtracting, by adding z, um, basically, and using the Sherman Morrison formula here called Rank-One formula. I suggested you can look it up. We can actually write the determinant of the quantity in the last equation of this slide exactly in a precise form. And this is useful because sometimes it gives you a way of bounding um, the the eigenvalues of the edge Laplacian. So this is an interesting formula, and you can find it in several books, including the one in our draft with the Viva. Okay, now that we have described all these properties of Laplacians for both the graph and the line graph, let's now start to discuss transition matrices. These are usually used in the case for Markov chains and for diffusion on graph. So how do you define transition matrix? If you define the transition matrix as D minus 1A, basically this is going to be a Markov chain, meaning that the sum of P over the rows is going to be equal to 1. Okay. Despite the fact that actually this matrix is normalized, the physics is basically contained. It's the same as the one by Laplacian. And in order to prove that, you can use the isospectrality we had discussed before, and show that actually the eigenvalues of P are very similar to the one of the original Laplacian, but shifted by a factor of 1. Okay. Um, so this is to say that actually then the original Markov chains and diffusions are very close, are very closely related. They are closely related for the following reason. So how do you define the diffusion operator on a graph? So this is defined as the following form: is an exponential of the matrix we defined before, this P diffusion matrix, which is the forward diffusion. P of t, where t describes say time, is nothing more than the evolution of probability on the nodes of the graph. P0 is the initial distribution of particles in the graph, and T defines the evolution of probability according to this diffusion. Okay. You might ask, what is the exponential of a matrix? It can be defined in several ways. In particular, it can be defined exactly in the form as a Taylor series in T of like exactly the exponential. And one question in my arise is what happens when t goes to infinity? This is important for several reasons, because very often there are diffusion in graph, say, can describe, say, the evolution of diseases among species or among individuals. It can describe heat conduction in discrete structure. So it has several applications. And the asymptotic probability basically tells you the equilibrium or the relaxation of the system. Um, and this brings us to the connection between walks, spectra, and the resolvent. Okay, so how do you make a sense of the evolution of a probability distribution of graph, given the knowledge of the spectra of the graph? Okay, um, so something. How do you define, first of all, the number? And in order to elucidate that, let's go and actually describe walks in detail. So the number of walks in a graph is pretty much bounded by the graph connectivity. Okay, so let's just start with some definition. Let's take first the power of the distance matrix A, say A to the k. Okay, if you go and think about the meaning of the power of um, A to the k, the element ij of this matrix, is nothing more than you do k walks, k steps on the graph, okay, and A to the k is basically the sorry, A to the k ij is 0 if there is no way that in k steps the particle is going to reach from I the node j. Okay, this element is 1 if there is only one way of reaching it, and it's more than 1 if there are more ways of reaching it. And it's not hard to see that this must be an integer number if A is a matrix and it only got 0 and bytes. Then, given this definition, the total number of complete walks is the sum over all the elements of the matrix Aij. Um, this will be the total number of edges of the graph multiplied by a factor of 2. If you define this the number of walks on the matrix A to the k, then nk is exactly the number of walks of length k. Okay. Now, it's not hard to it's not hard to see that necessarily the sum that is nk must be less or equal than the number of because this is we are defined as basically a trace in many ways. It's not hard to see that this is upper bounded by the degree of the graph. Okay, to the k. Okay. Um, Now that we have defined nk, let's start to introduce the generator of walks. Okay, and the generator of walks is given a certain parameter z. It's basically the polynomial where you multiply nk with z to the k and you sum over k. Okay, so why is this of any use? So if is say let's assume that k is very large, so this would be in the limit of an infinite number of steps. Then it's not hard to see that actually this is the definition of the resolvent. In fact, if you Taylor expand 1 divided by 1 minus x, this would be an infinite sum where you have the sum over x to the k, pretty much. And this is the same is true for a matrix. And in fact, you can actually show that the generator of random walks is actually given by the resolvent of the adjacency matrix. So which means here is a piece of notation: 1 divided 1 minus za is nothing more than the inverse of 1 minus za. And it's not hard actually to show that you can exactly calculate the generator of random walks as in terms of determinants as the last formula of this slide. And why is it called generator of random walks? Because you take a derivative to the k of z of this generator, basically this, and you set z to 0 after having taken the derivative. This gives you exactly the number of walks to the k. Something which is related to what I just described is, so you can describe walk also in terms of course, of the Laplacian. One property that you have is what is called, this describes, if you want, how hard or how complex is a graph, is what is called graph complexity, and it was introduced by Kirchhoff back in the days. It's a remarkable theorem, which I highly suggest you go and look up. It is defined as the number of spanning trees of the graph. Okay, and this is a measure of how many ways you have of how complex is your graph. Okay, and since it is defined in terms of determinant, it's not hard to see that this determinant of the Laplacian plus you add J, which is a matrix made only of ones, divided by n squared. This must be equal to the number, the product of all the non-zero eigenvalues of L divided by n. Okay. Here a comment must be, here we should make a comment. Note that actually this is a product of mu2 to mu n. The reason is that if the graph is connected, then the Laplacian has always 1, 0 eigenvalue. And you can actually see this from a formula that probably we had before. In fact, from this formula here, you can actually see that if you set x equal to 1 everywhere, then necessarily x, this formula here basically is equal to 0. Okay? And this is the fact exactly, this means x must be eigenvalue with eigenvector with eigenvalue 0 if x is a uniform vector, and these basically show that actually there is a number of eigenvalues. There's at least one eigenvalue which is 0 for the Laplacian. As it turns out, the number of 0 eigenvalues is exactly equal to the number of connected components, and when you calculate the complexity of the graph, then adding the matrix J divided by n squared is key not to obtain 0. Okay, I think we have discussed now how the resolvent of the almost the resolvent. This would be the z. In order to be the resolvent, it should be z on the multiplying 1, but it's close to it. In order, the resolvent to the density matrix basically is connected to the number of walks in the graph. Okay, so if you can connect or obtain spectral properties about the resolvent, you can actually learn some information about the walks in the graph. Something that is useful to know is that the resolvent has several properties. These are called the first and second resolvent equations. And these are properties between the resolvent at different values of z. And sometimes they're useful in certain calculations. I used them in a few times. Okay. One question that might arise is why, when is this matrix actually, which is again, I'm having some abuse notation here. A minus z1 is the inverse of the matrix A minus z identity. When is the case that actually this resolvent actually is unbounded, which means for which values of z is this resolvent going to infinity? And for this, you need to use what is called Fredholm alternative. Basically, Fredholm alternative describes the number solution on linear equation, if you want. and gives you, it's a very important theorem in linear algebra. And this shows that either you have a solution of the eigenvalue equation, or it must be true that the solution of the second equation here, um, the second equation here has a solution, unique solution V, which is a smooth function of D. Okay. Rephrased, this implies that the only times in which the resolvent is zero is for the values of Z, which is exactly the eigenvalues of the matrix A. So this is always bounded, unless you are in the points where the eigenvalues are present. Okay. Um, all right. So let's now write an expansion of the resolvent in terms of powers of Z. Um, so you see that basically if you expand this is going to give you some information about the walks, because this is exactly the sum of all possible um, um, non-zero, sorry, about all the possible walks of length k in uh, because it contains h to the k in the next expression. And this implies that for large walks, the behavior of the walk is connected, if you want, to the eigenvalues uh, of the resolvent in many ways. And the fact is that the resolvent is always a semi-positive matrix. So basically, this implies that in order to characterize the convergence of the random walk is basically the first eigenvalue for a simple reason that you can always divide the matrix by the first eigenvalues, and the other eigenvalues are going to be less than 1 and go to 0. So in many ways, the asymptotic behavior of your random walk is connected to the first eigenvalue, if you want. And how fast does it converge to equilibrium is basically connected to the ratio between the first and second eigenvalue, or rather to the difference. And in many ways, this is called, for reasons that are obvious, this is called the spectral gap. Okay. And in fact, we have this important result, which is, so suppose you have um, uh, put in order all the eigenvalues of the matrix A, or the distance matrix. Um, then the spectral gap must be bounded by the size of the graph, which in many ways this means that if you have um, at most if you have graph a number of connected graph of size n, you will converge in a number of steps which is of order n. Okay. All right. Also, it's not too hard to see that actually if you define another a number walk which is closed, so basically instead of, unlike before that we summed all possible ij's for the matrix aik, which was defined as mk, and you take the number of closed walks, then the number of closed walks, which is basically the trace of a to the k, is connected to the sum of the eigenvalues. Again, this is another reason to show, way to show basically that the number of walks is deeply connected to the eigenvalues of the matrix A. Okay, and in fact, you can define another generator for closed walks, and you can write a formula which is exactly the one before, is the one below, where rho are the eigenvectors of the matrix A. Okay. Now, well, this is important in the sense that it historically is a very important result. It is basically what I said before about the Laplacian. Here, I just want to say that Kirchhoff proved exactly that this formula, that determinant of L minus xi is the sum, can be written as the sum of the total number of walks, and this is exactly connected to the number of spanning trees of the graph. So again, This is another way of saying that the number of, if you want, the number of spanning trees is connected to the eigenvalues in the matrix L, which in turn is also connected, so before, to the adjacency matrix. So the takeaway message for this section is the fact that connectivity and eigenvalues are deeply connected, and that walks and the solvents are deeply connected quantities. And in terms, gives overall motivation for studying eigenvalues, because many of you probably are interested in walks and Markov chains. In particular, I suggest you go and look at the lectures by Naoki. Going back to walks, we know that A is a positive matrix, and we said before, and the controls, if you want, the long-term or the large number of steps walk is basically what is called the Perron route. Okay, the Perron route is the first eigenvalue of or the largest eigenvalue of the matrix A, and it's not hard to show that actually if you take the following limit, k to infinity, a to the k, r to the k, what you're going to get is a quantity which is exactly the right and left eigenvectors of a matrix which is connected to the left and right eigenvectors of it. Okay. It's not hard to show it. In fact, you can prove that all the eigenvalues are less than r, necessarily must go to 0. So what you're left on is only to with the composition, the tensor product, the composition described before, where you had for a to the k, r to the k, and since you're dividing by r to the k, the term is equal to 1. So necessarily you must converge to that. And this is true in general if the spectral gap is finite. Suppose you had a second eigenvalue which is exactly the same as the first, then how will you eventually get up in this limit a to the k divided by r to the k, and will end up with two elements that are exactly the same magnitude. So you will get the sum of 2. But the fact is, if A is a positive matrix, then there are some conditions for which there is a unique parent root, and this is usually the case if the graph is connected. Okay, I'll leave the description of all these parts actually to Naoki, but basically, it's the fact the long walk regime is also connected to, if you want, the degeneracy of the eigenvalues of A. And you can prove that if the graph is strongly connected, which means given a node I, you can actually visit all the other nodes J in finite number of steps. Then necessarily you must have only one root. Okay, and this is actually the statement of the Perron for Billing's theorem. Okay, the technicality here is that for matrix A, it has to be a non-negative reducible matrix. In terms of graph theory, this is basically the same as saying that the graph must be strongly connected, which is the definition I gave before. So what then if the A is a symmetric matrix, we said left and right eigenvectors might be the same. Then in this case, you can actually show that the Perron root is associated to a Perron eigen vector, which is the left eigenvector. Okay. This is another way of this is exactly what I said before, that you can write a to the s as lambda to the s, where you have this tensor decomposition. But because the Perron root is unique, then you're going to have a spectral gap, which is fine. I'll skip the proof of unicity. but and go directly to some properties of the parent roots. If you take the derivative of the parent root compared to a certain matrix element Aij, okay, and it's something that's legit to do, then you can there are these are results by Deutsch and Neumann, and they're actually used in economics. Then you can actually relate these derivatives to a certain matrix element, where R is the resolvent, basically, of the matrix A. Okay, you can find these results in the book. I strongly advise that you go and look them in detail there. One way of showing that if you want, for a macro chain, we have a unique parallel root is actually via this Fisher's inequality. And you can show actually that eigenvalues necessarily must be uh, upper bounded and lower bounded by the sum, the minimum, the maximum, the sum of the columns, and the minimum, the maximum, the sum of the rows. Okay. Um, for Markov chain, the parallel root necessarily must be equal to one because the sum of the columns must be sum to one. Another thing that you may ask is actually the solution of the following problem, and we're gonna see this in detail actually later in the applications. You might wonder when is it for z is it equal to one? So for the resolvent in which z you consider z is equal to one. When is the resolvent a positive quantity? And actually, this is, as some applications in economics in input-output theory, and these are some. There are several results about this particular question, and these in particular are called Hawkins-Simons theorem that says that if the operator I minus a, if A has all the principal minors positive, okay, then necessarily the resolvent to 1 minus A evaluated at Z is equal to 1 must be a positive operator. And this is a technical fact, but it's also connected to the eigenvalues of A, and you can actually show this. Okay. Here I would like actually to stop and basically I condense a lot of material in in only 1 hour, which means basically you will have to work on your own, work out the details. I'm gonna be available, so if you have some questions, just write on the group.